Okay, let me start recording. 1 second. Forgot about that. Oh, it's already recording? Okay, thank you. Okay, so it is my pleasure to welcome Dr. Sanjana Curtis. So Sanjana completed her PhD in 2020, so she's a COVID PhD, like a lot of us, at North Carolina State. She was working with Carla Fröhlich there. Then she went to the University of Amsterdam and worked with Dr. Philip Musta. And now she is at University of Chicago working with Alex G., who I'm sure many of us know. So she's an expert on kind of the microphysics of things that explode, like supernovae and neutron star mergers. So she's going to tell us a little bit about that today. So take it away, Sanjana. Okay. Oh yeah, wait, sorry, 1 second. If you're on Zoom and you have a question, feel free to unmute yourself. I don't know if I'm going to be paying attention to the chat, so just unmute yourself to ask your question. All right, thank you. Sorry, Sanjana, go ahead.
No worries. Thank you, Erica, for the introduction. Thanks a lot for inviting me to be here today. I'm really excited to be here, experience some topography again, coming straight from Chicago. So Erica already did this really great job, but I wanted to maybe say a little bit more about my research interests. And so I'm Sanjana Curtis. Today I'll be talking to you about the origin of heavy elements, specifically in compact object mergers. I'm a postdoc at the University of Chicago at the moment. My two broad fields are nuclear astrophysics and multi-messenger astrophysics. And so nuclear astrophysics being how did all the chemical elements around us come to be? The origin of these elements, astrophysically speaking, either in core collapse supernovae or in neutron star mergers. Both of these are systems that I study. I'm also working in multi-messenger astrophysics. So anything that explodes and makes a gravitational wave signal, if it also makes an electromagnetic counterpart, I'm interested in those electromagnetic counterparts. And the way I go about this is mostly through theory. I do lots of simulations, big and small, as needed to get at these questions. Okay. So my outline is very simple. I will tell you a little bit about heavy element nucleosynthesis in general, and then I'll focus on two systems: binary neutron star mergers, which can produce heavy elements, and black hole neutron star mergers, which can also produce heavy elements. And then I'll just tell you everything that I've told you. So here's a big picture at nuclear astrophysics, a view of nuclear astrophysics. What is nuclear astrophysics? Nuclear astrophysics aims to understand the chemical composition of the universe. And also locally, so the solar system, for which we have the most data. And the way we want to explore this is through an intersection of nuclear physics and astrophysics. We want to understand nucleosynthesis in these environments. Nucleosynthesis is the creation of new atomic nuclei from existing nuclei through nuclear reactions. And if you've heard of the famous quote that goes, "We're all made of star stuff" by Carl Sagan, this is the science of star stuff, nuclear astrophysics. And why do we care? We care because in a very broad sense, nuclear astrophysics is a search for our cosmic origins. Now today my focus is on heavy elements. This is the composition of a human body. All of us are this diagram right here. You won't notice a whole lot of heavy elements in there, but heavy elements are relevant to life. Things like iodine is an important nutrient. Our bones have some strontium. It's not important biologically, but it's there. Calcium kind of takes the leading role there. But if you look at other life forms, and on the right, you are looking at plankton. These are microplankton called acantharia, and they make their skeletons out of strontium sulfate. So if the human focus is not that interesting to you, do it for the acantharia. We have to understand how these creatures live and die. Okay, so what do we know so far? And here's a very big picture view at the periodic table of elements. All the elements are color-coded by where we think they came from, astrophysically speaking, the current understanding. And so if you look at something very light, like hydrogen, That's mostly made in Big Bang fusion. So a few minutes after the Big Bang nucleosynthesis happened that made hydrogen, helium, and a tiny bit of lithium. Then the entire story revolves around stars, supernovae, merging compact objects. So as you start looking at things like, say, titanium, about half of titanium comes from exploding massive stars, the other half from exploding white dwarfs or type 1a supernova. As you get to heavier and heavier elements, you'll start seeing that there's about a half and half contribution from dying low mass stars, so the yellow, and merging neutron stars here in this infographic. So merging neutron stars being the purple. And so you'll see some elements are almost entirely coming from merging neutron stars. And then things like gold, bismuth, polonium, and so on and so forth. So really, really heavy elements can be produced in neutron star mergers. So this is the big picture that we have right now. But the second you start looking at the details, that's where trouble starts. Okay. So since I'm focusing on heavy element nucleosynthesis, I'll focus on compact object mergers. When I say compact object mergers, it means either two neutron stars merging together or a black hole and a neutron star merging together. And so here's a schematic that shows you the general sequence of events in a neutron star merger. So the two neutron stars are in spiraling, approaching each other, emitting gravitational waves. They touch, and around this time, tidal forces will start ripping material off of the surface of these neutron stars, throwing it out into space. As they merge together, you can have a variety of outcomes. You can make a black hole immediately. That's this channel. So you have a black hole, or you have a black hole with a disk around it, an accretion disk around it, or you can form some sort of a temporarily stable object. So you can form a hypermassive neutron star that lives for some amount of time, and then it evolves either into a stable neutron star or collapses to once again give you this black hole disk system. So lots of possibilities here. And as all of this is happening, material is being ejected from the system through a variety of channels, through a variety of mechanisms, and all sorts of nucleosynthesis is possible in this material. It's neutron-rich material, but how neutron-rich? That is an important question. Okay, so the origin of heavy elements in these neutron star mergers, the way it works is through a process called rapid neutron capture. In fact, about half of the elements above iron are thought to be produced through rapid neutron capture, and neutron star mergers are just one identified site where this process occurs. What does it mean to say rapid neutron capture? This is just an atomic chart. These are different nuclei. On the y-axis is the number of protons in the nucleus. On the x-axis is the number of neutrons. In rapid neutron capture, these nuclei will capture a whole bunch of neutrons, one after the other, that will take them to very unstable neutron-rich isotopes of the same element. So for example, if this is zinc, you capture a lot of neutrons and you make a very neutron-rich, unstable isotope of zinc. This isotope will then decay. Through beta minus decay, it will convert neutrons into protons, and that's how it will climb up when you're talking about the elements. You make a new element. So you can also do this slowly and stick close to stable elements. And that's that low mass star channel that was on the periodic table. But rapid neutron capture, this is how it goes, very far from stability, in uncharted territory sometimes when you're thinking about the nuclear physics of these things. Okay, on the right, you're looking at the typical abundance pattern that rapid neutron capture is meant to produce. So this is the solar abundance pattern, actually. You're looking at amount of stuff versus the mass number of the nucleus. And so when you're looking at this The thing to notice is that there are 3 peaks. So around 82 or something, there's the first peak of the R process. Around 130 is the second peak, and around 190 is the third peak. So these are the 3 typical peaks that you would see when you calculate our process nucleosynthesis. And another interesting region is this region. This is the lanthanides, above 140 to about 180. Lanthanides are important because of how they affect the properties of the electromagnetic signal that you see. So if lanthanides are made in our process or not, affects the type of light that you would get from the event. Okay, so that's the full solar R process pattern. But every time rapid neutron capture happens, you don't necessarily get all of the elements all the way out to uranium. The amount of heavy elements that you get depends on one key parameter. And the key parameter is the electron fraction of the material. Electron fraction, which is the same as the proton fraction, because we're assuming charge neutrality. So electron fraction is the number of protons divided by the total number of neutrons plus protons. What this means is if your electron fraction is above 0.5, material is proton-rich. If it's below 0.5, material is neutron-rich. For rapid neutron capture, we want a lot of neutrons. We want the electron fraction to be low, below 0.5, or even lower, as low as possible, so you have a lot of neutrons to capture. Okay, so the electron fraction, if your electron fraction is above, say, is below 0.22, again, these boundaries are not clearly defined, but say around 0.22, then you can make the entire R process pattern. If your electron fraction is between 0.25 to 0.35, you might only make things up to this peak and a very small amount of lanthanides and then nothing beyond that. And if it's higher than 0.35, you might not make much R process at all. You might have very low abundances that go away as you approach higher A. So again, these boundaries depend on a few other things, but that's the basic idea. So below 0.22, you tend to make the full R process pattern. Above it, different things can happen. Now, the electron fraction itself, where does it come from? So neutrino-matter interactions control what the electron fraction is going to be. So in this material that's being ejected, that's through all these varieties of mechanisms, neutrinos are being absorbed and emitted. And these interactions can turn neutrons into protons and protons into neutrons. So you have to keep an eye on what neutrinos are doing, and you have to track what the neutrinos are doing to know what the electron fraction is. Okay, so neutrinos set the electron fraction, which sets the nucleosynthesis, which sets the nature of the electromagnetic signal that you would see. Here's just a fun movie of what nucleosynthesis looks like. And so I said a lot of things in words, but here's your rapid neutron capture happening and things decaying back to stability. I'll play it one more time just for fun. And then in the little inset, you can see the abundance pattern, the patterns that I'm trying to show you forming. So okay, here we go. Lots of neutrons are captured, and then beta decaying back to stability. And what you're looking at here is how much of a nucleus exists in terms of the abundance. And on the x-axis is the number of neutrons, on the y-axis is the number of protons, the same pattern that I showed you earlier in this figure. Now you're just seeing how much of various isotopes are formed and how they decay. Okay. Let's talk a little bit more about the electromagnetic signal now and what we can hope to learn from it. So I've set this up for you as your electron fraction, it's set by neutrinos. If your electron fraction is below 0.22, you make lanthanides, roughly. If it's above 0.22, you don't make lanthanides. But what does this do for us? Electromagnetically speaking, lanthanides, the opacity of lanthanides is such that they tend to absorb a lot of blue light. So if you make lanthanides, they will absorb blue light, and the kilonova that you will see will be in the red bands. So it'll be a red kilonova. At long wavelengths is where the flux will peak. If you don't make lanthanides, then you get a blue kilonova, an optical kilonova, and you're not worried about this selective absorption effect that the lanthanides are bringing. Okay, so the radioactive decay of these heavy isotopes is producing the kilonova. Depending upon whether you make lanthanides or you don't make lanthanides, you can get a red kilonova or a blue kilonova. So if we look at a merger event and we see a red kilonova from it, that tells us something about what kind of elements were created. It tells us that lanthanides, at least, were created. And if we see a blue kilonova, that tells us that lanthanides are not present. So you can hope to learn about nucleosynthesis by looking at this kilonova signal and its spectrum. Now, very luckily for us, this has already happened. And most of you are probably aware of the GW170817 neutron star merger event that was accompanied by an electromagnetic signal, that electromagnetic signal being the kilonova signal. And in this image, you can see sort of the kilonova at early times, about half a day, and being quite blue, and then fading and turning red at about 4.5 days after the merger. So we've looked at a neutron star merger event, we followed up the kilonova, and this is the kind of behavior that we've already seen for one event. And here's the data corresponding to that image. So this is the gravitational wave chirp. And this is what I was talking about with the red kilonova and with the different possibilities that the existence and non-existence of lanthanides can correspond to. And so what happened for this event is that at early times we saw a blue kilonova. At late times we saw a red kilonova. And usually the way this is interpreted is that the blue kilonova came from an ejecta component that did not have lanthanides, and the red kilonova came from an ejecta component that had lanthanides. So this is sort of like the two-component fit that people do, and this is how they explain the kilonova associated with GW170817. So what's the problem? The problem is neutron star mergers eject material in many different ways. So you have, as the stars are merging together, there's this tidal dynamical ejecta. These tend to be very neutron-rich, so maybe they make the red kilonova. As the neutron stars are merging together, they shear against each other. There's material ejected in the polar direction, which is shock-heated, and it tends to be less neutron-rich. Maybe that can make the blue kilonova. But we're not done. There's a disk that forms after the merger. There's material being driven off of the disk in through various mechanisms. Here it says viscous disk wind, through neutrino heating, through magnetic fields as well, this can happen. And so the nature of these disk winds can produce a red kilonova or a blue kilonova, depending upon what kind of electron fraction you find in this material. So this is actually a really messy system. And trying to match up these different components against the different kilonova ejecta components is a lot of work, and that's what people are working on right now. Okay, I'm kind of giving you a summary of my introduction now. The rapid neutron capture process, understanding the site of this process is key to understanding the origin of elements from iron to uranium. But as I've shown you, this field exists at the intersection of nuclear physics, atomic physics, hydrodynamics, nucleosynthesis calculations, being able to measure the spectra of different transients, gravitational wave astronomy. And then all of this information goes into actually understanding how galaxies evolve chemically, and then we get to trying to understand the solar process pattern. And of many possible sites, including black hole neutron star mergers, there's one confirmed site of the rapid neutron capture process. That's binary neutron star mergers, based on all this evidence that I showed you. But there are still many open questions. These two kilonova components, there's some agreement on where the red component might come from. The blue kilonova component, that early blue emission, is currently very unclear. We don't understand where that came from when you're thinking about the merger dynamics on all these ways in which material is ejected. What is the detailed nucleosynthesis? Looking at the spectrum of kilonovae and disentangling which elements are present is basically an impossible task. It's very, very difficult. There's a claim that there's lines of strontium that are detected. And then I think there was some talk about a couple of other elements, but that's all we can tell from the spectrum. And then depending upon how much material neutron star mergers produce, how much of it is neutron-rich versus not neutron-rich, all of this goes into understanding, are mergers the only site of the rapid neutron capture process? Are there maybe other other events that contribute, like special types of supernova could be producing heavy elements as well? So it is definitely not a solved question how rapid neutron capture occurs and where it occurs. And we are right now at a very critical point where we have this ability to measure all sorts of signals from merger events and then try to disentangle them. So it's like a really transformative time to be in the field and to be looking at these questions. Now, I already talked about why it's a little bit complicated. And even within all of that complication, here's the piece that's really, really messy, and it's the post-merger phase. So we actually have a decent-ish handle on how the dynamical ejecta look. But after the merger, you can have a black hole disk system and material being ejected from it in all sorts of ways. You can have a temporarily stable hypermassive neutron star. How long does this thing live? And how much material does it eject? And how it evolves beyond that point. These are all things that are currently very, very uncertain. The lifetime of the hypermassive neutron star and all the different ways in which material is ejected from these things and how much material is ejected as well. So this black hole accretion disk system, understanding this and understanding the hypermassive neutron star system, these are very important questions that are key to understanding heavy element nucleosynthesis. Why is post-merger uncertain? For a whole host of reasons. It's difficult. When you do numerical relativity simulations, they usually end at some number of milliseconds. It's very difficult to run these simulations and account for all the relevant physics beyond this point. The magnetic field gets amplified as the neutron stars are merging together. So we have to have a handle on how magnetic fields work, which we obviously have a great handle on. How the neutrino-matter interactions happen. This is a very complicated field because you can never, almost never solve exactly how the neutrinos are propagating through matter and how they're interacting. There's one simulation code that exists that can do this exactly, and everybody else has to use some sort of an approximation, and it all matters. The long-term evolution, so between this whatever number of milliseconds to maybe 60 seconds or days, or when the kilonova phase is actually attained, is a huge gap in understanding currently, because it's hard to run simulations for that long. And then, of course, all of the things that we don't know from nuclear physics. What is the neutron star equation of state? What are nuclear mass models, which Erica can tell you more about? and what are the correct nuclear mass models to use, and then neutrino oscillations. This is a piece that cannot be touched on in these type of dynamical simulations. It's a whole other study of how neutrinos change flavor and how that changes how they interact with material. So it's a computationally challenging problem. All types of physics is involved. There's unknown nuclear physics input, and then there's unknown physics altogether, like the neutron star equation of state. But all of this goes into understanding something like GW 17017 and its kilonova. Okay, so what am I doing about it? So let's get into two projects that I've worked on related to binary neutron star mergers and black hole neutron star mergers, starting out with the binary neutron star mergers. I'm asking two very simple questions. What kind of elements are made, and will the kilonova be blue or red? Very simple questions with very complicated answers. There are expectations from analytic modeling models for what you might see from, say, a hypermassive neutron star merger remnant ejecting material into space. What would be the nature of that material and the kilonova? There are expectations that exist. But are those expectations actually attained when you model these things in detail? And the hint is that no, is what we're finding currently. Okay, so let me get a little bit more into the GW 17017 kilonova to motivate what the purpose of the study was. So I told you that one way to understand the kilonova is to model it through two ejecta components, saying one component produces a blue kilonova, maybe this squeezed dynamical ejecta. One component produces the red kilonova. And then when you fit those models, you can get some estimates of how much material was in the red ejecta component, how much material was in the blue ejecta component, how fast these things were moving, and then what was the expected electron fraction. So just based on the presence or absence of lanthanides, you can roughly put that at 0.22 for the red component. So for example, here are estimates for the total mass of the red component, the velocity, it's sort of slow moving, and the electron fraction is below 0.2. It's very neutron-rich. That's what this is saying. So these are the expectations, and these are ideas for where the red component might be generated. It could be generated in the tidal dynamical ejecta. It could be actually disk winds. Maybe they are neutron-rich. But there are some ideas, and we are able to produce in simulations this amount of red ejecta moving at roughly that velocity and with roughly this electron fraction. So that's good. For the blue kilonova, we need to produce, based on this two-component model, 10 to the negative 2 solar masses of ejecta. So it's sufficiently massive that all of the existing ejection channels don't currently produce this much blue component. It's moving fast. Between 0.2 to 0.3 C is the velocity, and this is the estimated electron fraction for this component. So the question currently that a lot of people are trying to answer is how to produce this much material moving this fast that does not have lanthanides. And there are suggestions from different people about different ejection mechanisms. So for example, spiral density waves were suggested as one possibility. And the other possibility, which is the one that I've followed up on, was suggested by Metzger et al., saying that maybe hypermassive neutron star winds that are neutrino heated and magnetically accelerated, there's a reason for this, it is to produce this type of electron fraction and a very high total mass. So neutrino heated in order to get the electron fraction to be higher than 0.2, and magnetically accelerated, so they're moving fast, and there's a lot of ejecta that you will produce. These winds that emerge from a hypermassive remnant could provide that blue component that we're looking for that is currently not understood. So that's the follow-up study. The goal being to understand the electromagnetic counterpart to GW170817, the blue component of the kilonova, but also to understand what should we expect for future kilonovae. We may not be able to get a spectrum, but we might get a blue or a red kilonova. And what should it look like? Are all kilonovae going to look like AT2017 GFO, the name of the kilonova right there? So this study, you can find it on the archive. It's basically accepted in monthly notices. I need to click a button. And here what we've done is we've taken an outflows from a GRR MHD simulation. So it's general relativistic, magnetohydrodynamics is being done, and also neutrinos are being tracked. So all of the things that I've told you matter. And we've extracted the properties of the ejecta from a hypermassive neutron star from such a simulation, mapped it to a code that can predict the kilonova counterpart, and also calculated nucleosynthesis yields through a different method. But basically, based on realistic simulations, here are the nucleosynthesis yields, and here are the kilonova signals. The starting point for this kind of thing is a merger simulation. So these simulations, the two neutron stars that you see merging together, forming a hypermassive neutron star, this was done by David Radice. And then the hypermassive neutron star was taken from this simulation at about 17 milliseconds post-merger and mapped to a second code. And this is the evolution of just the hypermassive neutron star and the outflows from the hypermassive neutron star. That was done by Mosta et al. In GRR MHD. Okay, from left to right, you're looking at how the outflow from the hypermassive neutron star evolves in terms of its how unbound it is, for example. But there's a behavior happening. There's not some steady ejection that's happening. This is related to how the magnetic fields are pushing material off of its surface. So lots of material coming off of the hypermassive neutron star in the polar direction. That's what you're looking at from left to right. Now, the picture is great, but here is actually a histogram of the properties of this material. And remember, so the idea is to try to link it back to the blue component. So when we do the histogram, we're trying to see what's the total ejecta mass, but we're also trying to see are the velocities in the correct velocity range? Are the electron fraction values in the ejecta in the correct electron fraction range? So here in the ejected material, you can see there is a lot of stuff that's moving at velocities above 0.2, certainly above 0.1. So there is fast moving material in this ejecta component. That's good. The blue component is supposed to be fast moving. If you look at the electron fraction histogram, the electron fraction is between 0.2 and 0.3. That's also promising based on the estimates for the blue component. So things are looking good. But one other important thing is that the mass ejection rate is quite high. It's about 0.1 solar masses per second. So depending on how long the hypermassive neutron star actually survives, these ejecta could be so massive that the kilonova that emerges as a result of this outflow overtakes everything else, and that's your kilonova that you see. Whether that happens or not depends on the lifetime of the hypermassive neutron star, but what this is telling us is that hypermassive neutron star ejecta have distinct properties, distinct from other ejecta coming off of this very complicated system, and they're possibly dominant depending upon the hypermassive neutron star lifetime in terms of setting the kilonova emission. So they can't be ignored. That's the summary. You cannot ignore this. Okay, so how do we understand the nucleosynthesis in these things? The standard approach is to put tracer particles into simulation, post-process them with a nuclear reaction network. That's exactly what I've done. This is the outflow. This is the same outflow, but in tracers. You can see some sort of a YE distribution is color-coded in there. The electron fraction distribution is color-coded in there. So, okay, this is the calculation that we ran. And here is the result. So again, to remind you, the R process pattern and the solar R process pattern is this amount as a function of mass number. Here are the 3 peaks that I was mentioning at roughly 80, 82, 130, 180, something like that. And so when you compute the hypermassive neutron star outflow yields, you'll find that there's an order of magnitude difference beyond the second peak. If you match up to the second peak, you underproduce everything beyond the second peak by an order of magnitude, not just by a factor of something. So the third peak is underproduced. So lanthanides, this very critical range, you do underproduce them as we were hoping. So maybe this is all looking very good for the blue component. So let's run a radiation hydrodynamics calculation. Yes?
For the nucleosynthesis calculations, are you following just the YE, or are you also following the entropy of the material?
We are following the entropy, yeah.
Okay.
Yeah, so I focused on YE, but entropy and the expansion timescale, all of these things are important. And the nuclear reaction network does look at the evolve the entropy.
So there's some sort of thermodynamics in these models as well?
In the Skynet calculation, the tracer, yes. Okay. So they're heating and doing all of the things that you're supposed to keep track of. The temperature will change. Yeah.
Thank you.
Okay, and then let's run radiation hydrodynamics on these ejecta and see if you get a blue kilonova. And so again, here what you're looking at is something called the mass coordinates. Okay, maybe I should say, the way we did this is we set up a sphere of a certain radius in the simulation, and everything that crossed that radius and was unbound became our ejecta. And so now you can construct some sort of a profile for how the properties changed in these ejecta. So this x-axis is mass coordinate on both plots, which you can think of as the proxy for radius. So when you're looking at this, just think of it as radius. And on the y-axis here, it's velocity, and then the black line is the temperature. And so the point of this figure is just to show you that there's a lot of very chaotic temperature and velocity behavior. There's no nice power law that you can fit through these things and call it the ejecta profile. So you actually have to have a handle on what this looks like, because the velocities at least will matter a lot for the kilonova.
If you took a Fourier transform versus Euclidean?
I have not taken one there, but it has to do with how the magnetic field is becoming more or less efficient at throwing material out. So it's actually a little bit difficult to say, I would say. Yeah. Yes. Yes. So for this calculation, they have been averaged. So everything that crossed that sphere was averaged together to produce a spherically symmetric profile. But that is not the way to do it. This is a 0th order calculation. The geometry will matter. In fact, I think should matter a lot. And I'll get into that a little bit more. So again, these are spherically averaged profiles. So if you're looking at radius, and here's your electron fraction, for example, and the corresponding opacity of the material. One thing that you can see here already is that your high electron fraction material, your neutron poor material that does not make lanthanides is at lower radii. It's hidden behind a whole bunch of material that is neutron-rich, that does make lanthanides, and that will process, that will absorb blue light. So this is a spherically symmetric calculation right now. So there's no angle dependence in the jet included. but you can already see that there's some obscuration effect. And so what this does in the end is that we do get a bolometric light curve that peaks at roughly the right time scale for the blue kilonova. But if you look at the broad bands, the kilonova does not peak in the blue bands. It peaks in the red bands. And so what is the summary of all this work? I asked 3 questions. What kind of elements are made? 2 questions, and the third one I will expound on. The first being, what kind of elements are made? And I showed you that we don't get lanthanide production that matches the solar level or anything beyond lanthanides as well. So everything from lanthanides onward is underproduced. Is the kilonova blue or red? The kilonova is red. But you saw that a number of assumptions went into this modeling. In particular, the way we average things together could matter. Also, other things could matter. How long does the hypermassive neutron star actually live if you simulate with a different magnetic field configuration, magnetic field strength? Things could change. What happens actually long term? So these simulations all currently end at some number of milliseconds. Beyond that, things are still very fuzzy. So there's different ways in which ejecta components could evolve, could interact, could reprocess photons moving from one part of the ejecta to another. That's all something that we need to account for to really understand kilonovae. And the component that you looked at was just the hypermassive neutron star outflow. And that's already quite challenging to model. So detailed long-term modeling is something that's really crucial to truly answer these questions. Right now, with the best models of the merger that I could get my hands on, and the 0th order approximation that is actually quite common to do, we don't find a blue kilonova. Yes?
I mean, I guess I would say this is equivalent to looking at it edge on, probably, where the red stuff is sort of blocking. But we know from the observations, we know what the inclination was of the viewing angle.
Yeah.
There's more face on, or like 30-ish degrees.
Exactly, yeah.
I wonder if there's some way to reanalyze it, but have it from the correct viewing angles so we can address this efficiently.
Yeah, so that's the kind of follow-up that we'll have to do, because right now we're just assuming, average everything together spherically symmetric, but that's definitely not the case at all. So yeah, but it's tricky to know. I guess the easiest thing we could do is just shoot some tracer, like some lines of sight through the ejecta, and then reanalyze everything. Just looking at the composition in that direction. But yeah, that's going to have to be follow-up. Yeah. Okay. Moving on to black hole neutron star mergers. It's been a while, so I'll just remind you. Okay. Oh, wait. Okay. Again, it's the same 2 questions that I'm asking. What kind of elements are made? Is the kilonova blue or red? And once again, there's an expectation when you look at black hole neutron star mergers. There's an expectation that the material ejected from these systems will be very neutron-rich and always make a red kilonova. That is not necessarily what we find when we do detailed modeling. Okay, but now I'll remind you a little bit, since it's been a while, what a black hole neutron star merger looks like. So this time you have a neutron star approaching a black hole, getting disrupted by the black hole, settling in a disk around it. So a lot simpler than the whole neutron star merger mess that I showed you, but there's still dynamical ejecta driven by tidal forces, and there's still material that will come off the accretion disk through various mechanisms. One important thing when it comes to black hole neutron star mergers is that whether the neutron star disrupts at all is also a question you have to ask. Unlike neutron star mergers, where you always have some mass ejection, sometimes the black hole will just consume the neutron star, and that's the end of the story. And so whether the neutron star gets disrupted or not how much material gets thrown out dynamically, and how much material forms the accretion disk. This is something that's like a whole big parameter study that people have to do to get a handle on. And so whether the neutron star disrupts or not is a balance of the tidal disruption radius of the neutron star versus the innermost circular stable orbit of the black hole. And so this in turn depends on the properties of the neutron star and the black hole itself. So the mass of the black hole, the spin of the black hole, the mass of the neutron star, the radius of the neutron star, and how squishy the neutron star is, the neutron star equation of state. And people have generated these kind of figures where you just plot how much material settles into the disk and how much material gets thrown out as a function of these various properties. And so the first thing that we wanted to do when studying these black hole neutron star merger systems is to pick a few systems that make sense. And so we had to pick in good regions of this parameter space. And the idea that we went with was to try to produce very low mass disks and very massive disks, and sort of 4 total disks going from maybe like 0.01 solar masses to half a solar mass. The idea again is to model the nucleosynthesis. And we were also thinking Kilonova, but for now, I think the nucleosynthesis is so interesting that I wanted to show it to all of you, and we're already writing it up. Hopefully this will be out in 2 weeks. So if you see something on the, if you don't see something on the archive in 2 weeks, reach out to me. Okay, so check in on me. So this is, again, a very similar approach of taking ejecta from a black hole neutron star merger disk. So the post-merger phase, again, is the one that we're focusing on. And then calculating nucleosynthesis, calculating the corresponding kilonova. The merger disk simulation itself is done in GRR MHD. So again, neutrino-matter interactions are tracked. And the special thing about these simulations, though, is that they're done with the only existing code that can do Monte Carlo neutrino transport. So it actually exactly solves what the neutrinos are doing, as opposed to all of the other studies that have been done so far of these disks. Okay, so these are our disks. 4 disks ranging from light to massive, simulated with this new light code, the code that I just described. At the extreme cases, maybe half a solar mass of material can become a disk, which is a very dramatic thing if you think about a neutron star being disrupted by a black hole and about half a solar mass of it goes and sits in an accretion disk around it. And on the right, you're just looking at the density and pressure and temperature of these disks just at the start of the simulation as they were set up. From top to bottom, it's different disks. And from left to right, it's density, pressure, and temperature. But let's look at a disk evolution, because I think that's very cool. So you're looking at the disk sideways and top down. And the color is density, basically. So you can see material being thrown off of the disk, changing property, changing in terms of how dense it was or not as time goes on. And so basically, a lot of material is being ejected from these disks. That's the summary, and also it's a nice movie, so I wanted to show it.
Driving, or is it viscous?
So it's a variety of mechanisms, and so that's something that we're looking at in a follow-up study, because you have to look at the balance of these different things, and the magnetic fields are also involved. So there's like the magnetorotational instability is also playing into this. But yeah, there's a lot of material coming off of this disk. We started to characterize it, at least in terms of its electron fraction, the key property I've been going on and on about. So here in the figure, you're looking at how much material is ejected. From this way, you're looking at more material, so 10 to the negative 6 to 10 to the negative 2. And on the y-axis is the time. So you started out with almost with a very small amount of material, then there's this phase when you eject a lot of material as time goes on. Oh, sorry, yeah, as time goes on. And so then the structure of this outflow is on the right, and this is a little bit of a messy figure, but you're looking at angle off of the equator and the electron fraction as a function of time. So initially, this material that's below 10 degrees had an electron fraction between 0.25 to 0.3. And as time evolved, it actually dropped a bit to below 0.25. And this is what's happening at the equator. Out here, as you move away from the equator, you're looking at more and more protons. So the material is becoming less neutron-rich as you move away from the equator. And there's some particular time behavior. But in fact, I think it's really cool if you look at the 60 to 70 degrees, some of this material has become almost close to 0.5 electron fraction. So this stuff that was basically neutrons now has an almost equal number of neutrons and protons. And this is all coming from tracking the neutrino-matter interactions very carefully as we do this calculation. So this maybe goes to your question of what is the structure and does this matter? There is so much structure and it all tends to matter. But the first thing that we can do is try to bin the electron fraction, look at the histogram of the total ejecta. And so that's what you're looking at here for the 4 different disks. The only thing that I want you to focus on is there's barely any material below 0.22. That all the neutron-rich ejecta that's supposed to make lanthanides, we don't really have any compared to things that are less neutron-rich. And sure enough, when you get the nucleosynthesis calculation for this done, we find that the lanthanides are massively suppressed compared to the second peak, and none of this material contributes anything significant to nucleosynthesis beyond the second peak in these simulations. We can again look at, maybe in the interest of time, I'll skip this, but this is about the angular structure again. But anyway, so what kind of elements are made in black hole neutron star mergers? Only elements up to the second peak. Sometimes not even those, depending on how you look at the system. Is the Kilonova blue or red? We haven't carried out the Kilonova calculations, but just based on how suppressed the lanthanides are, and the fact that there's no real lanthanide-rich material to obscure these ejecta, my guess would be it's going to be blue. Completely opposite what we have expected and said up until now. So again, the final ejecta has to account for all the different components. So this was just the disk. There's still that dynamical ejecta component that's quite neutron-rich that will make the full R-process pattern. But from the disk, we are not going to make all of the heavy elements in black hole neutron star mergers, contrary to everything we've said so far. And again, this shows the importance of modeling these things carefully and including neutrinos, but also we're not done yet. There is a lot of detail and structure here, at least when it comes to the kilonova, that we still need to explore. And to do that, we need to model these things long-term beyond the few milliseconds that we are looking at. So let me just summarize everything now. Nucleosynthesis is a very interesting, exciting field. It's our connection to observations, multi-messenger observations, or observations of the solar system abundances, and to ourselves, to really get a handle on this question of heavy element production, we have to do detailed simulations that account for all of the physics that's relevant. Analytic models and back of the envelope calculations give us some sense of what to expect, but there is a lot of rich physics going on that we have to unravel. I've told you that from hypermassive neutron star outflows, we get a red kilonova, opposite of expectation. From black hole neutron star merger disks, we get a blue kilonova, probably, again, opposite of expectations, which shows that we need to model these things carefully, and we need to push forward still on the post-merger modeling phase, which is extremely, extremely uncertain. So this is not a solved problem, but it's an exciting time to be looking at this problem. And there are ways to make progress, and we just need to go ahead and do it. That's what I'm trying to do. And thank you so much for your attention today. And please ask questions as you wish. Thank you. Oh, quick shout out to everybody who has collaborated with me. So this was not all my single person's doing. This is all of the people who either contributed data or techniques or ideas or thoughts on this work.
Okay, thank you, Sanjana. Does anyone have any questions? I know we're kind of running late, but one or two quick questions. Andy? So we're being very tentative. Let's do Dahlia.
Thank you very much. It was a really interesting talk. I wanted to ask something very basic about the properties of the red and blue kilonova you described from observations.
Yeah.
So you gave there some mass estimate and velocity estimates for these two components. And I was wondering how these were derived from the observations.
Yeah. So I think that's basically fitting two separate models of basically if you had ejecta expanding this quickly with this composition, here's the light curve that you would expect, and then going and fitting that and seeing if you get the same to estimate a velocity. Does that make sense? And then the same thing for the blue component. So it's separately, sorry?
Just like cooling emission, this is what goes into?
Yes, basically. And I mean, it's our process heating and then how things cool down from there. Yeah.
It's radioactively powered, so the luminosity is going to be proportional to how much mass there is.
Yeah. And then the time scale to peak and all these things also depend on that. So yeah, it's basically there's a lot of heating before like 1 second or something, and then the heating kind of slows down. And then now you have expansion and all this material, all these photons escaping.
Thank you so much for a very nice talk. I have lots of questions, but maybe some interesting discussion. Like, so are white dwarf neutron star mergers not interesting at all for nucleosynthesis, or like why everybody neglects
White
them?
dwarf neutron stars, sorry?
Yeah, or maybe white dwarf black hole. I mean, I can think of many ways to create such merger situations, but nobody talks about them.
I think they're interesting personally. I think it's also a little bit of like, what are the rates of these things? So sometimes, you know, if you just don't make a lot of white dwarf neutron star binaries, then people are not that interested in what they're going to do. But I might be wrong, but I think they were suggested as a possible explanation for calcium-rich transients. Like they can make interesting transients, but not that many people are working on it. This is true.
Like nucleosynthetically, would you think of some cool elements to create from that?
That's a great question, and I don't have a great answer because it really depends on how the interaction proceeds. Because now the neutron star will begin accreting the white dwarf,
right,
and disrupting it. I don't know what that does. You should look at that. Yeah,
interesting.
But yeah, calcium-rich transients is the one I know that sometimes people look at. Yeah.
Okay, it is, well, it's past noon now. Does anyone want a quick question, Andy?
Yeah, I only have dumb questions. So, and I have a lot of them, unfortunately. But so this one, given your sort of most optimistic production of lanthanides,
Could you repeat that? I'm so sorry.
sorry, given your most optimistic production of lanthanides with the neutron star mergers, when do you need another GW17 to match statistics? Because you have masses, and now we need to reproduce our process elements in the Milky Way and in other galaxies. And when do you need another GW17, or is that not a good question?
When do we need? Well, from this, I'm not quite sure how to answer this. Let me think on this for a minute.
Well,
so
I need one right now.
Yeah, like
yeah, when does the statistics of the number of observed GW17 events become a problem because you're not seeing them?
Okay, I see. Yeah, so I think like seeing something like GW17 or 17 in that much detail is basically very unlikely to my knowledge. But there are enough neutron star mergers that the LIGO folks have estimated that we will see some potential kilonova in the next observing run. So, and especially with other telescopes coming online, like even JWST can look for kilonova and things like that. I don't know the exact rates off of the top of my head, but I think it's certainly not hopeless. There's a enough of a chance that everybody's following up on these. Yeah, that's the best I can do off the top of my head. Imminent. Yeah. Hopefully.
All right, thank you everyone for staying late. Thank you everyone on Zoom, and let's thank Sanjana again.
Yeah, thanks everybody. I am around if you want to chat. Thank you.
So I would say for our process considerations, well, this is one process. So let's.
Oh, hi.